The solvent plays a significant role in substitution and elimination reactions. Well, let's look at the idea of varying the solvent but keeping everything the same. If we keep the nucleophile the same and we vary the solvent as you see here, we notice that with methanol right here, the rate is 1. So it's very slow. But as we vary the solvent, we notice that the reaction rate is increasing. This is on the million scale, this is on a 1. So this would be over 1,000,000 times faster than the methanol. And for a simple reason here. This one right here has OH bonds, an OH bond. This one too. NH, so this one has NH bonds. This one does too. But this one right here, which is we call DMF, dimethyl formamide, and this one has no, and this is important, no NH bonds. So they're all polar, by the way. Even this one. But we see that when we have no NH bonds, that would actually increase the reaction rate. And for what reason? So aprotic, in this case, there are no OH, NH, or HF bonds. Remember, those are, if you recall, those are hydrogen bonds. This would make, again, SN2 reaction faster. So polar aprotic solvent is, again, they have no, as I defined here, no NH or OH, NH, HF bonds. And polar protic solvent, of course, they have OH, NH, HF bonds, or FH bonds. Here are some examples. You have acetone, you have dimethyl sulfoxide, we usually call it DMSO, acetonitrile, dimethyl formamide, like the one we just examined, and HMPA. Just be aware of some of these polar aprotic solvents, and polar protic solvents, just look for, again, the OH, NH, HF bond. So we saw that in methanol, like here, we have an OH bond. In water, we have the H2O bond. In ammonia, if it's aqueous, again, we have the NH bonds. In formamide, right there, we have NH bonds. So be aware of those. The question is why? Or even those here. So as we said, it's faster. The reason why is because Cl as a nucleophile needs to be free to attack. Otherwise, what's the point of the nucleophilic substitution reaction if the nucleophile is unwilling to attack? So you have to make it freer to attack. So if you have DMSO, if we use DMSO, versus water, and we look at DMSO. DMSO has, I'm going to draw just a few. Right here. If you notice here, what you have is you have CH bonds. So those are non-polar. So that means if we even draw just one of these CH, remember the CH bonds are non-polar. So there's no delta plus delta minus on it. So in this case, your Cl minus is poorly solvated, right? Meaning it's not surrounded by those solvent molecules, despite, having delta minus and delta plus on S. But there again, the S is very far out from the Cl. Whereas if you have water, look at this now. It would be surrounded heavily. And this is the key. These drawings are meaningless without putting the delta pluses on H. So I'm going to use a different. So look how this chlorine, which has the chloride, which has a negative charge on it, is surrounded heavily by this hydrogen bonding, right, by water, right? And then it's preventing it from attacking. So there, imagine as it's moving, those water molecules are moving with it, and they're preventing it from attack because, again, there is a polar bond between them. Also, what's good about having DMSO as a solvent is that they are very effective, very effective. They're very effective at surrounding the cation and prevents it from going back and bonding ionically with the chloride. Delta minus, delta minus, delta minus. So it holds this cation that solvates it. It holds it in place and prevents it again from going back and bonding with the Cl minus. So that's the point of using polar aprotic solvents.